Maybe I should, maybe I've gone through too much material in the last 2 lectures. So perhaps I should slow down and go back instead of doing something different, new. So why don't you start asking questions? So then I can, because while SU2 you are very familiar with from the old times, not from the quantum mechanics course. Not SU2, SO3, but they are very similar. And the level of Lie algebra is identical. But SU3 is new, so maybe I've gone too fast. So please ask questions.
Actually, about myself, I didn't study the CSE. I mean, I understand pieces of it, but the big picture is not clear. So maybe when I study, I will collect my thoughts and know at 10 point exactly what is that I don't understand. But for the time now,
at the moment you don't have specific questions. Okay.
Exactly.
Yeah. I mean, so let's see. What was I doing anyway last time? SU3 algebras. Okay, so again, let me start repeating. I repeat some of what I've said already, and then towards the end I say some new things also in the new material. So the first of all, so I'm given some Lie algebra, G. Huh? So Lie algebra. So the first step, and this will be, I mean, although I have not defined, it will be of the form of the type semi-simple, which we'll discuss. We'll define this later, what we mean by semi-simple and so on. Because in order to define that, I need to introduce some new concepts. But for the moment, okay, the SU3 and SU2, etc. are semi-simple algebras. I turned it on, yeah. I turned it on. Yeah. So the first step here is to find a maximally commuting, maximum, this is important, maximally commuting set of subalgebra. Okay, this is in general it's not an abelian algebra. This is not abelian. SU2. I have in mind SU2, SU3, right? At the moment. Then we'll generalize it later. So both SU2 and SU3 are non-abelian. So keep in mind SU2 and SU3. So both are non-abelian. So the first step then is to find a maximally commuting subalgebra. This subalgebra is called Cartan subalgebra. Subalgebra. Okay. So in the case of SU2, we took it to be the one-dimensional subalgebra. This Cartan subalgebra was a one-dimensional subalgebra generated by sigma 3. We just chose it. It doesn't have to be. Could have chosen sigma 1 or sigma 2. Doesn't matter. But the point is that whatever, if I had chosen sigma 3, then I cannot include sigma 1 and sigma 2 in this algebra, right? Because sigma 1 doesn't commute with sigma 3, right? So this was a one-dimensional. That is why it was one-dimensional. On the other hand, in SU3 case, we had H1, the two-dimensional subalgebra generated by, say, what we were calling H1 and H2, right? Or, yeah, you could choose any basis, it doesn't matter, right? So what were they? These were just a diagonal 3x3 matrices, which were SU3 matrices, SU3 Lie algebra generators. This is also diagonal. We just chose it to be diagonal because it's convenient. It doesn't have to be. Okay. So we choose this H1 and H2. So they generated by it. So the arbitrary element was alpha H1 plus beta H2, or we call it AH1 plus BH2. This is an arbitrary element where A and B, for all A and B, say, for example, let's say real numbers. So this is actually subalgebra.
It cannot be complex.
You can also make it complex, it doesn't matter. Yeah, you can also make it complex for the moment. Real and complex. Of course, at the end, we will, in the SU3, what we have is a real. In the real SU3 that we defined. No? Real meaning the Hermitian, Hermitian generators. Okay. In that case, I cannot multiply by complex numbers. No. Real numbers. But as I said, when we talk about Eigen Functions, and you need to complexify, because in general, even if you have a real matrix, Eigen Functions may be complex. No, so you need to go to the complexification. Okay, so that's so why are we doing this? Because then the idea then is to find in any representation for this Lie algebras, find the Eigen Functions with respect to the Cartan subalgebra. No? Since these are maximally commuting, you can simultaneously diagonalize. Okay? This is not a very precise statement, but it is true in these cases. In the cases that we are considering, you can diagonalize them.
Okay. Not precise because we didn't say that they are Hermitian.
Okay, if they are Hermitian, yes, of course, yes. But I'm saying in general. In general, it is not. You need to do a bit more than that. So since these are Hermitian, therefore they are surely you can diagonalize each one of them, and since they commute with each other, you can diagonalize simultaneously.
In the fundamental representation.
Sorry.
In the fundamental representation.
In the fundamental representation is already diagonal right from the beginning. Both of them we chose to be diagonal, right? But this should be true in any representation. If in that representation you can realize H1 and H2 as Hermitian matrices. So in particular, so in all representations, in all at least, let me just, I'm not being very precise here, but very mathematically rigorous. But okay, in all representations, one can simultaneously diagonalize. The Cartan subalgebra. Let me give a name to it. Cartan subalgebra. Cartan subalgebra C. Every element of the Cartan subalgebra can be diagonalized.
If for any representation, the elements of the Cartan algebra are mapped to the elements of the Cartan algebra of the other representation?
No, the representation, of course, there is no concept of a Cartan subalgebra of the representation itself, right? It is, I think what you mean by the following. In any representation R, okay, I call it R, it may be some n by n matrix, right? I've not used n anywhere. Okay, n by n matrix. So this will be some n-dimensional representation. Okay. So this representation you can think of. So whenever I have a n by n matrix, I can think of it as acting on an n-dimensional vector space, right? So this will act on some n-dimensional column vector. So that you can think of this matrix as making some transformation on an n column vector, right? So you can always think of these Lie algebra elements. If you succeed in constructing a representation, then you can think of this Lie algebra as making some transformation on an n-dimensional vector space. Right? That is how it will always encounter these algebras in physics. Right? In physics, what will happen? There will be some n-dimensional representation of a given symmetry algebra, right? And then and all of these Lie algebra elements will make some transformation on this vector space by just multiplying this matrix. Right? So that's how these vectors will transform, right? And then you have, for example, if you want to construct an action which involves these vector spaces, then you want to construct some combinations in the action which are invariant under this transformation. Because we are thinking of these transformations as some symmetry transformation. It should be a symmetry of the physical problem. No? So therefore the corresponding action, corresponding Lagrangian, this must be invariant under that symmetry. That is the purpose. That's the purpose of, and this is what we always encounter. So when we talk about standard model SU3 cross SU2 cross U1, you'll have various fields, quarks and leptons and so on. They'll be transforming under different representations of the SU3 cross SU2 cross U1. Okay. And what you want to construct is some kind of an action, right, involving all these quarks and the gauge fields and maybe some scalar Higgs particles, all these things. And then you construct something which is invariant under this SU3 cross SU2 cross U1. If it is not invariant, it's not a symmetry of the theory, right? So then we are not even interested in that. No? We are interested in symmetries of the theory.
Is there a relation between reductible representations and symmetry?
No. I mean, not directly. No, it's not. I mean, symmetry is okay, a physical principle, right? Now, So what happens? So since you said it, or maybe let me come back to that a little later, because at the moment I'm still trying to. I will come back to that later. What's the difference between irreducible and reducible, first of all? But let me first discuss this a bit more. In particular, there is one representation. There are actually two representations which are special. One, of course, is the defining representation. This is so because again, all the Lie algebras that we'll be interested in are matrix groups, are coming from matrix groups. SUN is the n by n, SUN group is a n by n unitary matrices with determinant equal to 1, right? So the definition of these groups itself involves matrices. So that's what we mean by matrix groups. Okay, so that is the defining representation. So for example, for SU3, defining representation is 3 by 3, right? Because already the initial definition was in terms of 3 by 3 matrices. So those 3 by 3 matrices will act on a 3-column vector and make the transformations there, right? So this is usually called fundamental representation. That's already there. It is already given to you. You don't have to do any work to construct this representation, right? But then the second, which is completely universal for all the Lie algebras, completely universal, is what is called the adjoint representation. This adjoint representation is very important for us, because it's not only that it comes freely. I mean, it comes for free given the Lie algebra, but more importantly, it captures all the features of the Lie algebra. The commutation relations. Commutation relations are the basic feature of the Lie algebra, right? Those commutation relations are encoded in this algebra. In this adjoint representation. Okay. Because you remember, adjoint representation is simply, you can just use a structure constants to construct those matrices, right? So the adjoint representation captures structure constants, and therefore the full, the Lie algebra, the properties of the Lie algebra. So this is quite important. And then, of course, there will be all sorts of other representations, which could be reducible or irreducible. Irreducible or reducible. Adjoint representation itself also in general can be reducible. Okay, can be reducible in general, but not for the kinds of for the simple Lie algebras. They are not reducible. For the class of Lie algebras we'll be discussing is in fact not even semi-simple. We'll be actually focusing on simple Lie algebras, which I have not defined either of them, but just wait for maybe next week I will define this. So the examples of simple Lie algebras are all of these: SUN 2, 3, 4, etc. for any n going from 2 onwards. These are all examples of simple Lie algebras. But semi-simple Lie algebras would be, so I remember I keep mixing the notation. Since I'm talking about algebra, I should not use a capital S, but I should use small s. Capital S will stand for the group. Okay, so these are simple Lie algebras. Or for example, you can take SONs, SON. But this is for n equal to 3, not 2. N equal to 2 will be SO2, which is an abelian algebra, right? That doesn't fall into the category of simple algebras. So starts from n equal to 3, but not n equal to 4. So somehow 4 is removed, and then everything else. It happens because SO4, it's a accident that SO4 in fact is a direct sum of 2 SU2. Direct sums. So it's not a simple algebra. It would be semi-simple, but not simple. Semi-simple. So semi-simple are the ones which you start from the simple algebras and take direct sums of them. Okay. Then you get semi-simple algebras. Okay. So this would be a semi-simple algebra, SO4. That's a very particular case. It doesn't happen for others. And then we'll see others. I mean, these things you are familiar with. SUN are given by n traceless Hermitian matrices. These are given by n orthogonal, matrices. So this is those things are there. There are also something which you are familiar with, and we'll be talking about later. You are familiar with symplectic groups, no? From the canonical transformations. You must have studied in the classical mechanics, no? When you go from Lagrangian formulation to Hamiltonian formulation, so you introduce the canonical variables x and the p. P is the momentum, no? And they satisfy the Poisson bracket. And then you look at the set of canonical transformations, they preserve this Poisson bracket, no? So that is the symplectic groups, and the corresponding algebras are symplectic algebras. No? So we have not discussed that, but I will be discussing it next week. No? So just to the symplectic algebras, it is usually denoted by SP for symplectic, SPN. So there are all this infinite series of Lie algebras which are simple Lie algebras. Okay. And then you can get any semi-simple by just taking direct sums. Okay. That's why we will focus on the simple algebras, because if you understand simple algebras, then of course we have understood semi-simple algebras, right? Because semi-simple are direct sums of these different algebras.
What about E8 groups?
Yeah, E8 groups are exceptional. Yeah, there are. I'll be discussing it. You see, next week what my plan is to go to the general discussion about the Lie algebras, not the specific SU2, SU3, but in general. So I'll define what is simple algebra, and then the consequences of that, and then then it turns out I don't know whether I'll be able to reach up to that point by the end of the course, but there is a complete classification of simple algebras, and that involves basically the SUN, SON, SPN, symplectic, SPN. These are the infinite series because n can be arbitrarily large. These are infinite series. But apart from that, there are some exceptional Lie algebras. There are a few of them. E6, E7, E8, F4, and G2. I think that's all. I think there are only 5 exceptional Lie algebras. But they are not for any n. There is some specific E6, E7, E8, F4, and G2. Okay. So they appeared. I mean, the complete classification. So this mathematician sat down and said, okay, they start from the general structure. Then you know that given a Lie algebra, it puts various restrictions on the possible roots, the possible kinds of roots you can get. And then from that, they just try to understand, irrespective of the Lie algebra and so on, just, okay, I have a set of roots which satisfy these conditions. What is the most general way I can construct these roots? Without referring to any Lie algebra. Okay. So you understand, the logic is this. So you start from the Lie algebra. You go to the roots, okay? And then starting from the assumptions that go into the Lie algebra or simple Lie algebra, you derive various properties that the root satisfy, the root system satisfies, no? Then you forget about the Lie algebra and you ask the question, okay, I have got some vectors, root vectors, no? Roots, I mean, in some dimensional space, and they satisfy these conditions. So what is the most general thing I can construct? No? So mathematicians, and they found that, surprisingly, that there are more possibilities than these three series. These three series we knew the early algebras, right? Some more, a few, which was E6, E7, E8, E6, E7, E8, and from F4 and G2. That's it. They found that you can construct a root system which corresponds to some new types of algebras which were not in this class, and they gave a name to this: E6, E7, E8, F4, and G2. Okay. So okay, this is how. But that's a complete classification. You know, there are nothing else. There's no other simple algebra. This is very powerful, actually. Very powerful classification theorem.
Was it done by Cartan?
Actually, who did that? Maybe it's Cartan. I'm not sure. Yeah, Cartan is one of the persons who is around in this field. I mean, everywhere you see Cartan, but I don't remember who did that first. Probably it's Cartan. Cartan classification. I think it's called Cartan classification, right? I think, yeah.
Do these groups also have applications in physics?
Do
they still have applications?
those except this E8, E6, E7 enter crucially in string theory. String theory, yeah. In particular, E8. E8 appears very crucially in string theory, and G2 appears again quite in a different way. G2 appears. Yeah, I mean it's. You know the. Okay, maybe I can take 5 minutes to just mention something about it. You know, it's the string theory, or superstring theory. Superstring theory lives in 10 dimension, 10 space-time dimension. Okay, 9 space, 1 time. Okay. That is where, I mean, consistency of the superstring theory implies that you must be living in, if string theory is correct, which means correct means what? Not logically correct. Logically, everything makes sense, right? But it may have nothing to do with the real world. That's no. But if it has something to do with the real world, then the real world must be 10-dimensional.
Right? So I think there is a commutator that has to be 0, and for that to be 0, you should have 10 dimensions.
Yeah, correct. Yeah.
Because of ultraviolet variances, right?
Well, ultraviolet, I mean, even forgetting about all the quantum corrections, that has to do with the quantum corrections.
Yes.
Already the classical level, you cannot construct the string theory without, in other dimensions.
Yeah, because of the weird anomalies, no?
Because of the anomalies, yeah. But anomalies from the point of view of the
classical theory.
there are two classical theories here. String theory itself is a two-dimensional quantum field theory.
Yes, conformative.
Two-dimensional, right? But that two-dimensional theory is not the quantum theory of the. I mean, that two-dimensional quantum theory is already a quantum field theory, but in 2 dimensions.
Yes.
Okay.
It was on the string worldsheet.
String worldsheet, yeah. So exactly. So there, I mean, it's even a construction of the Hilbert space of states. Forget about all the interactions and so on. Already the level of Hilbert space of states you cannot construct unless you have this. You cannot have a positive definite Hilbert space. When you have Hilbert space, you want positive definite norm, right? If I take a state, it must have a positive definite norm. No. But in these theories, including Gates theory, even usual field theory, in Gates theory, it is not guaranteed that you have always a positive definite norm. Okay, you have to do a lot of work to construct a positive definite Hilbert space. You have not done field theory, so I don't know. Okay, I think.
I think in some QED there is something that your A0 doesn't have a positive.
Exactly. I mean, So it's okay. Yeah, I mean it's. The commutation relations of the A mu, you see, any field, phi with phi dot, Poisson bracket, this will be replaced by the commutator, right? Phi dot is basically the momentum. No? So similarly, you have A mu and A mu dot. That Poisson bracket will be something given by eta mu nu, because that is the only Lorentz covariant object, right? But then you see that if I choose a signature, eta 0, 0 is -1, because there's a difference between 0, 0 and the remaining guys, no, I, j, k. So the space part. If I choose the space part to be positive, the time part will become 0, 0, negative. right? And that negative means that you got negative norm Hilbert space coming from, when you apply creation operators of the A0, you find negative norm states. So you have to, and of course that can be understood, that is understood because there is some kind of gauge symmetry, and you have to use a gauge symmetry. No? I mean, this is happening because of the gauge symmetry. No? So you can also cure this problem by using the gauge symmetry. That's fine. In string theory also the same thing happens. There are some, in the commutation relation you find there is some negative objects appear. Okay, so a priori, if you consider the string Hilbert space, it will have infinite number of negative norm states. Okay, but then you have to use the symmetries of the string theory, and the symmetries are what? I mean,
Symmetry,
diffeomorphism, right?
And biosymmetry.
Diffeomorphism and bisymmetry, exactly.
Uh-huh.
So you use that to cure this problem.
Yeah.
But then you find that at the quantum level, but not quantum level of the field theory, of the quantum level of the two-dimensional theory, okay, there are two quantums there. One is the quantum two-dimensional quantum theory, which describes to you a classical, I mean a tree-level string theory.
Yeah.
Okay, but then you have to also quantize the string theory. That is the different second step. Huh? But already the first step, you see that this dimensions appear. The critical. These are called critical. This is called a critical dimension. Okay, and then what you do? So this is. I mean, I don't want to go into too much detail because this it will take me away completely from this. The whole thing comes from G2, right? Now it turns out that at least there are several types of superstring theories. There is one theory which is called A, other is called B. Type 2 A theory and B theory. This one can be understood as coming from some 11-dimensional theory. Okay,
And theory.
just call it. you all know a lot. I mean. So it's called M theory. Okay, but of course our real space-time is 4-dimensional. So what do I do with the extra dimensions? So the idea is extra dimensions must be too tiny that we don't see them. You know? So very, very tiny. So but it must be some. So if I start from 11-dimensional theory and I want to come down to 4-dimensional theory, which is what our real world is. So the remaining 7 dimensions must be some compact space, you know, which are so tiny that our experiments are not able to notice them yet. So this 7-dimensional. So then the question arises: what kind of 7-dimensional space? Calabi-Yau would be in this case.
Okay.
So from here, if you go to 4-dimension, then you have a 6-dimensional internal theory. That internal theory is supposed to be Calabi-Yau. Calabi-Yau, if you require some properties, you want some properties in 4-dimensional theory, right? So similarly, if you want some certain properties in this theory, then you need to choose some specific 7-dimensional compactification. This procedure is called compactification because you are compactifying some directions to make them compact, close them. So this space is a 7-dimensional space, a compact space, which is very closely connected to this G2. Okay, it turns out to be the holonomy group of this space. Okay, as another word, but okay, there's some word called holonomy. At the moment, just holonomy group. Okay. I mean, to understand holonomy, you have to first study the general relativity (GR) course. Okay. It's basically the idea that if I start at a point, I mean, some curved space, I have some curved space, right? I take a point, start from a point, and consider going around and come back here. Okay. Now, if you take some vector here, some tangent vector, there's some compact space. I mean, some curved space. It's not a flat. I'm drawing it on the blackboard, but you should imagine there's a curved thing, something curved. Now, if I take a tangent vector here, okay, at this point, and as I go around, I parallel transport this vector. Okay. When I come back here, what's going to happen? If this space is flat, then this vector, when I transport in a parallel way, there's a notion of parallel transporting. Okay. When I parallel transport and I come back here, I come back to the same vector. But if the space is curved, then that will not happen. in general. Okay? In fact, when it comes back, if this part is curved, then it could be that it has come back to some other direction. Its magnitude will be the same. One can show that when you do the parallel transport, its magnitude doesn't change, but the direction can change. Okay? So now you consider all possible curves, all possible closed curves, starting from a given point. For each curve, maybe when I go through this curve, it comes back with a different direction, and so on, right? But since the magnitude doesn't change, it will be some orthogonal group rotation. The length doesn't change. So this rotation will be given by, if suppose this is n-dimensional, then this can be given by some SON transformation, right? In general. Okay. So now consider, holonomic group is what? Is consider the set of all closed curves that you can draw in this space, right? And then consider the set of all these vectors which appear here, right? So all of these will be given by some subgroup of SON, because every such rotation is an element of SON. Right? So for a generically curved space, the holonomic group will be the full SON. For a flat space, where the space is flat, no curvature at all, then the holonomic group is identity, because every vector comes back to itself, right? But you can have in-between spaces, no? Where holonomic group is neither the identity nor the full SON, but some subgroup of SON, no? And it turns out that in this 7-dimensional theory, this 7-dimensional space must be such that the holonomic group is actually G2. So that's how the G2 appears in the N theory, in the corner. So there is space for F4. I don't know. F4 I have not seen so far. I'm sure there must be something hidden behind F4. I have not seen this F4 appearing in a crucial way in any of these.
E8 appears the most.
E8 appears directly in already in 1984. People realized the E8 appearance of E8 in string theory. And once you have E8, all of these come because these are subalgebras of E8. So they all come.
And you can recover the standard model.
Yeah, then you can. This is the granulification theory. So there's a whole concept of, even for SU3 cross SU2 cross U1, much before string theory, people had already started looking at this idea of unification, because this SU3 cross SU2 cross U1 is not a complete unification, right? After all, because you have an SU3 interaction, SU2 interaction, and U1 interaction, right? And these have different strengths. You can choose a different strengths of interaction, couplings, what we call couplings. Coupling of the U1, coupling of the U1 is a charge, basically, electric charge, no? Coupling of U1, SU2, SU3, these are all independent couplings, no? So some people already in the late 70s or even mid 70s, they started thinking about how would it be that, you take a big group inside where SU3, SU2, U1 sits, and perhaps the theory is that this big group, which somehow breaks down to SU3 cross SU2 cross U1 when you come down to low energy. So this was the idea. Okay, this idea was old idea actually. It still is. People are still working on it in various groups. So. Yeah.
Is the holonomic group always a group? Could it be a subset of SON?
It will be some subgroup of SON.
But it's always a group.
It will be a group. Yeah. It has to be a group because you see, look at all the set of the vectors you get, right? Now I can do the following. So now let me draw it in different way. So let's suppose that when I go around this, my original vector was that. When I go around this path, this is rotated to something here, right? Now suppose when I go around this path, okay, then this original vector is rotated to this. Now consider, since we said the set of all closed paths, right? So suppose I consider now another path which is this, going around here, and then coming around here, right? So then it will be the product of these two. This was one SON, that was another SON, right? Then the product of these two elements will again, because if I go around this and this, then I will get the product of these two elements, right? So you see the group structure will appear there. That way. Anyway, this is all, I mean, okay, so I should get back here. So I will discuss this. I will, not next week. Next week is the last week? No, I have one more week, right?
Yeah.
So the week after, I will discuss this part. Okay. Fine. So that was a strategy. So what we'll do is we look at the adjoint representation, okay? And an adjoint representation, we will that's what the whole discussion was yesterday and I think day before yesterday. So that we look at the adjoint representation. But adjoint representation means what? So if I look at adjoint action of H1 or H2, so one of the elements of the cartan, then that is the same as acting on some other generator X, some remaining generator X, or any generator X. This is nothing else but by definition Hx. Right? That is how the adjoint representation is defined. Right? So if this X happens to be, so the first case is if X happens to be inside the cartan subalgebra, then of course this commutator is 0. Then this is 0, right? Because they commute. That was the definition of cartan. But if the X is in the remaining part, then the idea is to find combinations of this, find X's such that this gives you back again some number times X. Right? That was the idea. So this is what that we are trying to look for the Eigen Functions. And this is possible because this is possible to do for all the H because this is all the cartan subalgebra, because every element commutes for the other element. So they are mutually commuting. So you can simultaneously find Eigen Functions for all of them. You see. I mean, so you see, remember, so I have two generators for SU3. So I have H1 and H2. Both of them, we are requiring that this gives me some number, I don't know, say X1 times X, and this gives you some X2 times X. Right? In general, this may not be possible, but it's possible here because H1 and H2 commute. No? I mean, if I just give you two arbitrary element, not just a cartan element, some arbitrary element, I cannot diagonalize. I cannot find mutual simultaneous Eigen Functions. So that is where cartan is appearing. And from this analysis for SU3, SU2 was trivial. SU2 was H was sigma 3, and the other two elements were simply what we call sigma plus minus, right? These were Eigen Function, sigma 3 with sigma plus minus gave, I don't know, maybe 2. I think, yeah, in this normalization maybe 2 plus minus sigma plus minus, right? Okay, that is how we get it. Now here we have here there is only one eigenvalue involved because cartan subalgebra is generated by one element. But here we have two independent cartan generators. So there are these eigenvalues are labeled by two numbers, right? So therefore this you can plot in a two-dimensional space. Unlike here, where here I can just plot in one-dimensional. So we have the 0 eigenvalue, which is the H itself, sigma 3 itself. Sigma 3 commutes with sigma 3. And here, okay, here you'll have 2 and a minus 2. Okay, if I don't divide by 2 here. I think previously we were dividing this by 2. That's why this was 1, no? Okay. So this is the thing. So this corresponds to sigma plus, this corresponds to sigma minus. Okay. And we saw that this was giving an SU2 algebra with the commutation, with the commutation relation that sigma 3 with sigma plus gives you sigma plus, and so on. Sigma plus with sigma minus gives you that, sigma 3, right? That was the algebra. Is that everything? Please stop me if there's any question. Stop me immediately. Okay. Now here this will be plotted in 2. And what we found, we found x alpha 1. So there are 6 eigenvectors you can find: x alpha 1, alpha 2, x alpha 3, and the minuses of them.
The number of eigenvectors is always constrained by the dimension of the group.
That's right.
So they all form a vector space.
Yeah, from the vector space, because Lie algebra has the same dimension as a group. No? And so in this case, what happened? Cartan, so total dimension was 8, of which 2 were the Cartan, so subtract that, so you get 6. The remaining space is generated by 6 elements, right? 6 vectors. So those 6, I can find combinations from those 6 to construct these Eigen functions. So any element of the original SU3 can be expressed as linear combinations of these 6 of them and the 2 of them, right? 2 Cartan and the 6 non-Cartan. Huh? So that's the right. Now the nice thing about this was that from this picture, from these things, you can immediately see that inside SU3 there are lots of. So what are the commutation relations? These commutation relations were fine. So what was it? We had H. If H is AH1 plus BH2, you had X alpha. H commuted with that was simply alpha H, X alpha. Where then we had the explicit formulas for what is alpha 1H, alpha 2H, and alpha 3H. No? Yeah. I think let's just write down alpha 1H was 2A minus B, alpha 2H was minus A plus 2B, and alpha 3H, I don't remember, was it A plus B? I think A plus B, something like that. Okay. Okay, I can look it up, but it's something like this. So now, so that is fine. So this part is so this kind of relations give you commutation relation between some element in the Cartan with the remaining, right? But then we also had commutation relations of X alpha with X beta. Okay. Now, of course, one could work it out explicitly, but one thing you can immediately see, and that is that we use again and again, crucially, we use this fact again and again, that whatever this is, I mean, these roots add up, is additive, right? And that is simply because if I take H and take the commutator of this with that, then using Jacobi identity, we see X alpha. This is crucial actually, so it doesn't matter if I keep repeating it. X beta. Okay, just use Jacobi identity, and that tells me that this is simply alpha plus beta H. X alpha X beta commutator. Yeah. So this is a Jacobi identity. I use Jacobi identity here, and here I use this this relation. And these are numbers, so I can take them out. You get this standard procedure. So the important point to remember here is that when I take the commutators, the roots add up. Whatever you get here, the roots add up. So whenever I take this commutator, question is it, you can ask the question, this commutator is something, I don't know what it is, but whatever it is it an eigenstate of the Cartan, adjoint representation of Cartan? That's the first question. Answer to this question is clear. I mean, this calculation shows it is an eigenvector. Right? And not only that, it also tells you what eigenvector. It is alpha plus beta. So it's just additive. It adds up. Right? So from this we conclude immediately that so X alpha. So the general structure of the commutation relation is X alpha X beta is equal to 0 if to the several possible. One more thing. Now, what happens when you have X? So let's take the case here. So I assume that alpha plus beta is not 0. Okay, and alpha plus beta is not a root. Is not a root. Not one of the roots that already exist. These are the roots: alpha 1, alpha 2, alpha 3. So if alpha plus beta was not one of these, okay, then it must be 0. This answer must be 0, right? Because there is no such die. in your system, right? There is no such thing. Okay. On the other hand, so there are two possibilities here. If alpha, I am assuming alpha plus beta not equal to 0. So one possibility was this, and second possibility was alpha plus beta is a root, is one of the roots, any one of these. Okay. Then it is not 0. It will be simply that. It will be x alpha plus beta up to some number. Okay. Up to some number, it will be simply x alpha plus beta. Okay. And finally, the last case is when. So this was the whole thing was for alpha plus beta not equal to 0. Now, if alpha plus beta equal to 0, then what happens? X alpha x beta, x alpha x minus alpha. That means beta is minus alpha. This is going to be inside the kappa. Right? Because anyway, the alpha minus alpha is 0, so it has 0 root, which means the kappa algebra commutes with whatever you get here, right? So it must be in the kappa. Now, of course, it could have been 0, right? Because 0 is also inside kappa. But this is one fact that in the SU2, SU3 case, you can explicitly see that this is not 0 and it's in kappa. Whatever it is in kappa. Okay. We will discuss next week when we do more generally for all simple algebras that this can never be 0. Any questions? Yeah.
That these commutation relations are derived only from the observation of the generator.
For the SU2, SU3, yeah, those matrices that we have from there, yeah, just the commutation relation there, yeah.
I mean, can this be derived from any general way?
Which one? Which statement? This statement?
Yes.
The fact that it is not 0.
Yes.
That's what I will do in next week. No? Because yeah, next week we will see that if your Lie algebra is simple Lie algebra, then this can never be 0. Alpha with the same minus alpha.
Then what about the apart from
also this, all of these things one can derive generally. Yeah. Yeah. For the simple Lie algebra you can derive generally. But for SU3 you can just check it explicitly. SU2 and SU3, because we have those matrices, we can explicitly check, and that answer is not 0. Yeah. But next week or yeah, maybe towards the end of next week, I will start discussing this.
I have one question. H1 and H2 are linearly independent from the x's.
Yes.
But then if x alpha and x beta give you 0, they commute, they should be in the Cartan algebra.
No. It's a maximal set of commuting, mutually commuting.
Yeah.
I mean, you see, you already chose H1 and H2, right? Now, your question is, could I have add x alpha in this set?
Yeah, because it commutes with x beta.
Yeah, but no, we want to the sub-algebra.
Okay, I see. So
It is not just taking two elements and they commute with each other, no? It should be a sub-algebra. Yeah.
When we say that alpha plus beta is not a root, does that mean that there is no linear combination of the x alphas that will give me an eigenvalue alpha plus beta when I act to the adjoint edge? Does that mean this?
Yeah, correct. Yeah. I mean, so here you see we had six remaining guys, right? So okay, there were some roots. Alpha 1, 3 different roots and the negatives of those roots. That's it. This one we have already done. There's no room for anything else, no? Because the total dimensionality is 6. So in each Lie algebra there will be, so for example if I go to SU4, let's say SU4, what will be? The Cartan will be 3, because if we look at the 4x4 traceless diagonal matrices, Hermitian diagonal matrices, there are 3 independent, right? These are 4x4 matrices. Defining representations, you define as 4x4. So this 4x4 matrices, Hermitian and traceless, right? And trace equal to 0. So if I take the diagonal matrices, Hermitian means they are real. Okay, and tracelessness means that the sum of these entries must be equal to 0. That means there are 3 independent. 3 independent diagonal ones, right? If this condition was not there, then there will be 4 independent. But because of this condition, there will be 3. So Cartan subalgebra, there will be 3-dimensional, right? In the SU4 case. Like in SU3 case, there were two diagonal traceless generators, right? Which we are calling H1 and H2. In SU4 case, there will be 3. In general SUN case, n-1, right? So those will be that will be the dimension of the Cartan. But what's the total dimension of this space of the SU4 Lie algebra? Is 4 square minus 1, which is 15, right? 15. So these are in the Cartan. The remaining 12 are not in the Cartan. So those remaining 12 will give you non-zero roots, right? For every root, there's a negative root also. So there will be 6 distinct roots. Right? Okay. So like that for all the algebras. Okay. Fine. So this fact is very important because in particular this one here, that it is not equal to 0. For the SU2 case, what was happening? I can just write down the SU2 case. SU2 case, we had this commutator. So we had alpha 1, alpha 2, alpha 3. So x alpha 1 with x minus alpha 1 was H1, right? X alpha 2 with x minus alpha 2 was H2, and x alpha 3, x alpha minus alpha 3, x minus alpha 3 was, I think, I'm not sure, but H1 plus H2, I think. Yes. Huh? Okay. So there were these 3 things. And now you see that this immediately implies that there's an SU2 subalgebra, you see from here, right? So SU2 subalgebra here generated by H1 x plus minus alpha 1. This is one SU2 subalgebra. Okay. Because if you look at the full commutation relation, this with that is that. H1 with x alpha 1 gives you again x alpha 1, because that was by definition the root, right? H1 will, and similarly H1 with x minus alpha 1 also gives you back again x minus alpha 1. So this forms an SU2 subalgebra. Here similarly this one forms another SU2 subalgebra plus minus alpha 2, and this one here H1 plus H2 comma x plus minus alpha 3. So you have these 3 different SU2 subalgebras. Okay. And then we also plotted this thing. I mean, it's easier to see the whole what is happening if you draw a picture. So it was something like this here. Alpha x alpha 1, so the root alpha 1 here, let's say alpha 2, okay, and then you had this minus alpha 1, and then you had this alpha 2, alpha 3. This is just a nomenclature, it's not important, you can choose any name. Minus alpha 2. So this was, here I have plotted not the eigenvalues of H1 and H2. I mean, this is nice picture. It was plotting there's a particular combination, I think H1 minus, no, that what we call Y. So here is Y and plotting. That is just a plotting, it's not important. That's how I'm plotting the graph. No? It's not important. All right, so now from here you see that we are saying that this forms an SU2 subalgebra. By this I mean x alpha 1, x minus alpha 1, and the H1. Because here it's 2-dimensional. This is the Cartan, right? Zero eigenvector is for the Cartan because Cartan commutes with itself. So here they are like sitting like two guys, H1 and H2, linear combinations of them. The 2-dimensional space. Here is 1-dimensional space. At each of this point there is a 1-dimensional space, right? Because if I say that the x alpha 1 has this eigenvalue, I can multiply this by any number, no? That will also have the Eigen function. So each of them is a 1-dimensional space. There's a 1-dimensional space, 1-dimensional, etc. But here you have a 2-dimensional space. Because the 0 root means Cartan subspace, right? So So when I say something like this, that this is an SU2, there's an SU2 here, I mean X alpha 1, X minus alpha 1, and H1 part of it. Not the full H1 and H2, H1 part of it. Okay? When I say that this one is an SU2 subalgebra, I mean X alpha 2, X minus alpha 2, and H2 part of it. Right? One dimensional subspace of the Cartan. Okay? And similarly. Now this is very important, very useful for us, because now we can see, I mean, how, let's focus on this SU2. With respect to this SU2, okay, this itself is an adjoint. So X alpha 1, H1, and X minus alpha 1. This is an adjoint of the SU2. Then what is left over? You have X alpha 2, X alpha 3, X alpha 2, X alpha 2, let's say X alpha 3. That is one, two of them. Then you have X minus alpha 2, X minus alpha 3. And finally, we have the H2. Right? That is all. I've just split the eight basis objects in terms of this, in this group. Now, this is an adjoint representation of this SU2 subalgebra. Okay? This is a doublet of SU2 subalgebra. This is another doublet of this SU2 subalgebra, and that's a singlet. Okay? So this 8 splits into, is not H2, I think this is another guy, it's be some combination of H2 and H1. Probably it's what I call Y. Okay? Another combination. This will be a singlet. So this 8 splits into 3 plus 2 plus 2 plus 1. With respect to this SU2 subalgebra, this SU2 subalgebra. Okay. Why that's so? Because you can see, again, use the additive property. Right? When I take the commutator of this with any of them, any of these guys, I will get something whose root vector will be the addition of the two roots. Right? So if I take X alpha 1 with X alpha 3 commutator, this vanishes because the sum of these two roots would have been here somewhere. You add up these two vectors, it should be somewhere here, right? But that is not part of your roots, right? So that is in this situation when we said that it would be alpha plus beta is not a root. So that is 0. So that commutator is 0. So this is a highest weight state with respect to this SU2, right? X alpha 1 is the raising operator of this SU2. And this is annihilated by the raising operator. So this is the highest weight state with respect to that SU2. Okay. But now if I apply X minus alpha 1, which is the lowering operator for this SU2, then you see what I'm going to get. Now I have alpha 3 and minus alpha 1. You add these two vectors, you get there. So it exists. So it is in this situation. It exists. I mean, alpha plus beta exists, this root. And that is in fact X alpha 2, right? So in other words, what we are saying is if I start with X alpha, if I look at this system, X alpha 2, X alpha 3, this system, this is the highest weight state with respect to this SU2 because it's annihilated by the raising operator. And when I apply lowering operator, I get X alpha 2. And that's it, it stops there. Because if I apply another X minus alpha 1, I would go there. But this root doesn't exist. Okay? So we see that there is a doublet here. And the same thing you can do here. This will be a doublet. This will be the highest weight state because if I take this sum doesn't exist. And then when you apply a lowering operator, I will come here. So there will be a doublet. And then there is, suppose, another combination. Here I've chosen only one of the Cartan subalgebra. Right? There will be another combination which will commute with all of that. In fact, you can see which one. Actually, the Y commutes with everything. Right? So that's why this Y is singlet.
What is Y in this diagram?
No, both H1 and H2 are, I mean, if we are using this definition, right, the H with the anything, X alpha, we are saying is alpha H, X alpha, right? So in particular, if I choose this to be again some H prime, then it is 0, right? So you see that, I mean, for two of them, for in this two-dimensional space, in the two-dimensional space, the roots correspond to roots are usually one doesn't call it a root. Usually people don't think in terms, call it root. Okay, roots are always called the non-zero ones. But it's understood that when I take, so if I look at the commutator of x alpha 1 with x minus alpha 1, okay, which is in this situation, alpha plus beta equal to 0, then what I'm going to get is some element in the Cartan subalgebra. No? That is because the Cartan subalgebra will have 0 eigenvalue. Okay. So since eigenvalues are additive, alpha 1 minus alpha 1 is 0 eigenvalue. So it is a full Cartan subspace here. Right? But when you take this particular commutator, I'm going to get one combination of the two-dimensional Cartan subalgebra is two-dimensional. Right? But when I take this commutator, I'm going to get one particular combination, which I call H1. Okay. Here, this commutator will give you another particular combination, H2, which I call H2. Okay. And these two will span the Cartan subspace, okay, which is two-dimensional. Yeah. Okay. So this kind of pattern is always there. And I told you that this is a lot of, it's a very, very tight situation, you see. Because here because I have not only just one SU2, I have 3 SU2s. So all this whole picture should be also compatible by looking at the other SU2s, right? So for example, I could have started investigating this SU2. Well, under this SU2, these are forming a doublet, right? This is forming another doublet. So it is so tight. That is why there is the requirements are too much here. No, too much requirements. That everything, all of these states must fall into some representations of these 3 different SU2s, which is a pretty tight, very tight condition. So that's any more questions on the, let's say this is a review of the last 2 lectures.
Just want to be sure about something. Well, if alpha plus beta is not a root, how can we be sure that it will be 0, not going to some other place?
Well, this has to be an element of the Lie algebra, right? So, but for the Lie algebra, these are all the roots I have found. No, there's nothing else exists. So the only way, the only possibility is it has to be 0, right? Yeah. Or if alpha plus beta was 0, we could not conclude it, because then, strictly speaking, this is not a root, right? This is 0. Zero root we call it, but it's not a root. But all it is saying, this argument is saying, when we say is additive, it is just saying that how the H acts on that. Because the roots have the information about the eigenvalues, which means eigenvalues of H. So when we say something alpha plus beta, like in this case, so what we are saying, right hand side, whatever it is, it must commute with the H, with any arbitrary H of the Cartan. But then it could be some element of the Cartan, right? So that is what happens. So all that we can conclude from the general argument that the roots are additive. And when you take the commutation relation, they just add up. This tells me that, okay, the answer is this, sum is 0. But that means it commutes with the H, the C, the Cartan subalgebra. Therefore, this can only be an element of the Cartan subalgebra. Right? And the second statement I made was that how do I know this is not 0 actually? No, and that happens for simple Lie algebras. You can prove that, which we'll discuss next week or end of next week. Yeah. Any other question? Please, because most of you are seeing this for the first time, so these things are, unfortunately, you see, this course is very condensed. Like 4 lectures a week is a bit too much. Because many of these things you require to think. It's not just, kind of, it has to sink in, no? It takes some time. No. So think about any question you have.
Yesterday I said to you that tomorrow you can tell me about the formula.
Which formula?
The dimension.
Okay. So if we have finishes, so far I was discussing adjoint, then let's go to the other representations. So now how do we construct for the fundamental representation again, which was a 3 by 3 matrices, we constructed the weights. So for the fundamental representation, this was easy because already the 3 by 3 matrices for the H1 and H2, which were this. H1 was that, H2 was 0, 1, minus 1. Okay, everything else 0. Okay. So these are already diagonal, so I have to do no work to find the eigenvalues, right? Eigen functions, because it's already diagonal. And the eigen functions will be simply the 3 eigen functions, let's say E1, E2, and E3. This will be simply 1, 0, 0. Because you remember, this is acting on a 3-dimensional vector space, right? So that I can choose this basis, and in fact, this happened to be the eigen functions also. It happens to be because these are diagonal. So I don't have to diagonalize anymore. This is what it is. So the eigenvalues for this were, so if I look at, W1 of H, say H is again A H1 plus B H2. Well, just apply A H1 on this, I'm going to get A times 1, right? A, and when I apply here, this gives you 0, right? B times this acting on that gives you 0, because there's nothing in the first row. 0. Then W2 of H, W2 is a E2 for the things for A. This is now, if I apply, so it's minus A, because if I multiply A, so minus A times this one, so it's minus A, plus B, because this is B, is a plus B times that, so plus B. And finally, W3H is, so this one, A doesn't give you anything, and this one gives you minus B. So these are the weights. These are the weights. These are called the weights. So the roots are nothing else but the weights for the adjoint representation. So weight is a more general thing. Weight is for any representation. So this is the weights here. And if you again plot it here, it comes out to be something like this here. So let me put here something like that. Something like this here. Something like that. So this is the three stages, W1, W2, and W3. In this picture. I mean, this is in the, I plotted with a Y. So you cannot read from there directly. This is, I have plotted, this axis represents a Y quantum number, Y eigenstate. Y was a particular combination of H1 and H2. Is that confusing you? I mean, because I use the H1, H2 all the time, but when I plot it, I always plot with the H1 eigenvalue here and Y eigenvalue there. Yeah. I hope, I mean, really nothing will change. I mean, if you just plot H2, except that these pictures will be a bit distorted, but nothing will change. So that was the fundamental representation, and then the complex because you see this, unlike the roots, roots were symmetric under the, I mean, for every plus root there was a minus root, right? So when you remember when we went to the complex conjugate representation, R of any x was mapped to minus R bar of x, right? This was defining complex conjugate representation. In particular, if you look at R of H, H is the karta, this implies that this is the same as minus, this goes to minus R bar x, R bar H. But RH is real, because this RH is simply just this. This is the matrix. These are all real matrices. RH is real. So when you take R bar is the same as R. So there's just a minus sign. So both of these guys flip the sign, which means the eigenvalues will flip, right? But when you flip the eigenvalues, then what will happen that this point will go somewhere there. I mean, minus of this somewhere there. I don't know. Let's put a circle here. This point will go there, and this point will go there. No? So we have this triangle here, and here there is this triangle. So that's the difference between 3 and 3. This is called 3-dimensional, 3 represent. This is just a notation. The original representation is denoted by 3, and then this representation denoted by 3 bar. This is a notation. So you see, unlike SU2, in SU2 every representation was self-conjugate. If you take the complex conjugation, you get back the same. That was because the eigenvalues are equally distributed in positive and negative, from plus j to minus j, right? So when you flip the sign, it doesn't change. It's just a reordering of the states, no? Which means just a change of basis. But here it becomes completely different in SU3. So the complex conjugate representation is not the same as the original representation in general. For adjoint, yes, it is true. For the 3, it is not. 3-dimensional representation, it is not. Okay. But now let us go to the most general. So this was fundamental, and that was the adjoint. But now let's consider the more general representation. How will I construct representation? In SU2 case, I know how to construct the representation. We discussed that in detail. You just specify the highest weight state. Highest weight state, which will have some quantum number j. J3 eigenvalue will be some j, let's say, in the highest weight. Then you just start applying lowering operators and construct the full 2j plus 1-dimensional representation. We can do the same thing here, except now it's a little bit more complicated because I have lots of raising and lowering operators here. So what is the general idea? General idea is to see, one thing you notice here in this picture, that x alpha 3, if you look at the commutation relation of x alpha 1 with x alpha 2, it gives you x alpha 3 up to some number. Okay? That is because this alpha 1 root, alpha 2 root, when you add that up, you get x alpha 3. So right hand side is going to be proportional to x alpha 3. Okay? What does mean? It means that and similarly, of course, x minus alpha 1 with x minus alpha 2 gives you x minus alpha 3 again some number. So what it's telling you that it is sufficient to just focus on these two SU2 subalgebras, alpha 1 and alpha 2, because x alpha 3 I can always think of as acting, as an application of this SU2 and that SU2 on a given state. I don't get any new information. If I start from some state, let's say some state, I apply x alpha 1 or x minus alpha 1, x alpha 2 and x alpha 3. So, and I apply various, various elements, alpha 1 of this SU2 subalgebra, x minus alpha 1, etc., or this, for example, let's take x alpha 2, x alpha 1, So what I'm going to do, I will take a state and apply all the possible generators of these two SU2s, of this SU2 and that SU2. Okay? So arbitrary number of x alpha 1, so an arbitrary number of x minus alpha 1, x alpha 2s and x minus alpha 2. Then what I'm saying is that then I don't need to worry about x alpha 3, because after all x alpha 3 is nothing else but the commutator of these two. Right? I don't get any new state by applying x alpha 3, because x alpha 3 acting on this state is nothing else but x alpha 1, x alpha 2 acting on that state, minus x alpha 2, x alpha 1 acting on that state. I should really put here the representation, but I kind of am being sloppy. Yeah. in that representation. Right? Sorry. This is true because if this is true, then in any representation this is also true, right? The commutation relations are present in the representation. So therefore I can just forget about this third SU2 subalgebra. I can just work with the two SU2 subalgebras. I'm not losing any information. That's what I'm saying. I'm not losing anything. Okay. So what we will do here is we will just label. So a state will be labeled by the highest weight state. Highest weight state of SU3. We will define it as the highest weight state of these two SU2 subalgebras. Okay. Or these two high. So the highest weight of SU3 is the same. I mean, we define. So we define as the state which is the highest weight with respect to say these two SU2s, x plus minus alpha 1, h1, h2, x plus minus alpha 2. These two SU2s. Okay. So what does it mean? I will consider it, so highest weight state, highest weight. I don't know how shall I call it. HW. HW means highest weight. Highest weight state should be annihilated by x alpha 1 and also should be annihilated by x alpha 2. HW should be equal to 0 in that representation. Again, but this of course automatically ensures that x alpha 3 also annihilates it, because x alpha 3 is nothing else but this Rx alpha 3 is nothing else but that. But Rx alpha 2 annihilates the highest weight, and this also annihilates the highest weight, so this is 0. Right? So it is sufficient to just ensure these two conditions, and it's automatically satisfied the x alpha 3 also. Right? So you don't have three different conditions, you have only two conditions, three independent conditions. You only two independent conditions. Third one is automatically satisfied. Okay. So this will be the starting point, and so we define this. Now, where is this here? Now this picture. Okay, let me use this a bit. Now after that, now we just follow what we did for SU2. For SU2, we know that I can specify any number, j. Let me use a 2j instead of j, because then I'll always talk about integer. Because here you see, just to match the two, because in the discussion of SU3 we were using sigma 3 by 2 as a katana, right? And of course then the eigenvalues would be, or this would be j, m, where m could be integer or half integer. No? So r sigma 3 by 2, we were calling this as the h. Right? Here in this SU3 language we are actually just calling sigma 3 or analog of sigma 3. I mean h1 was 1 minus 1 0. This is part is sigma 3 but not sigma 3 by 2. No? So there's a factor of 2 compared to SU2 conventions that here there's a multiplication by 2. Okay. So in SU2 case, highest weight, in the SU2 case with this convention, the highest weight was given by j, any j which is integer or half integer, and m content number will be just j. Right? But that was this content number. If I multiply this by 2 to go over here, then what it would be? This will become 2j, right? I mean, this m will become twice. It is convenient because then we never have to worry about the half integers. Everything will be integer. Okay? But of course, this integer means if integer is odd, we are talking about spin half. I mean, half integer integer plus half spins, and if this integer is even, then it means integer spins. So just it's a multiplication of the factor of the spin by 2. So that becomes easier to okay. And indeed here we are already multiplied by 2. So here automatically you will get integers. But that is not the spin. Spin will be half of that. Okay, so so in the SU2 case, what we did, we just specified any integer. I mean, if I had used sigma 3 rather than sigma 3 by 2, I would just specify any integer, right? And for any integer, there is a representation. Correct? Irreducible representation. So here the generalization is for SU3. Now, since I have now 2 SU2 subalgebras, I have to just specify a simultaneous highest weight with respect to these 2 SU2s. So I start that, and then, so if I have found this highest weight, then I can ask what is the eigenvalue of this highest weight with respect to H1, RH1, and RH2. These are going to be some integers. So this will be some integer, let's call it, I don't know, N1 times highest weight, integer. Remember, because I have multiplied by 2, not half integers, integer. And RH2 acting on this highest weight will be some number, integer N2. Again, I mean, in the previous normalization, this would be integer divided by 2. Integer divided by 2, but now it's integers. So the claim is that you give me any set of, I mean, this of course, N1 and N2 are positive, I mean non-negative. Non-negative because this is the highest weight. Highest weight will have always positive eigenvalue, right? Non-negative. So you give me a pair of non-negative integers, and there exists a unique highest weight, irreducible representation. So this exactly analogous statement. Like for SU2, we said, give me any non-negative integer, there is a spin, that there is an irreducible representation.
So here the highest weight rates are indexed by 2 integers.
Highest weight? Sorry?
Rates are indexed by 2 integers actually.
Yeah, exactly. This will be the general story. So how many integers were needed? Because you see the roots, the Cartan subalgebra was 2-dimensional. So every root, so you had 2 eigenvalues for every thing, no? H1 eigenvalue and H2 eigenvalue. So that is why we were able to draw the roots in a 2-dimensional space, right? Because there are 2 quantities I had to give. If you go to SU4, Cartan subalgebra will be 3, so there will be 3 independent Cartan generators. So there will be 3 independent eigenvalues, right? For each vector, there will be, to specify the eigenvalue, I need to specify 3 numbers, right? So that will be drawn in a 3-dimensional space. And again, in that case, you will find that you need to, you can pick 3 SU2s there, such that everything else can be expressed in terms. Just like here, the X alpha 3 could be written as this commutator. It will turn out again in the SU4 case, if you can take you'll have 3 SU2s, and then the commutators of them will give you everything else. Okay. And this is general case. If you take SUN, rank will be n-1. I mean, the Cartan subalgebra will be n-1 dimensional. The roots will be drawn in an n-1 dimensional space, right? And in that case, you will have n-1 SU2s to specify. And then everything else you can express in terms of their commutators.
For SUN, we have n-1 Cartan.
N-1 data, yeah. You need n-1 data to specify which representation you're talking about here.
Can you prove that for SUN we have n-1 Cartan?
Yeah. I mean, as I said, all the general discussion will be next week and so on. Yeah.
Is it more convenient to use Y instead of H2?
Well, you can use Y, but it's not very useful. I mean, it is more useful to think in terms of 2 SU2 subalgebras. So if you take alpha 1, x plus minus alpha 1 with H1 is an SU2 subalgebra. And if you take x plus minus alpha 2 with h2, that's not y, you see, h2 which is subalgebra.
So then we have to make the connection with what, then y is more convenient.
Yeah, then you can plot. So I could have plotted all these things with these eigenvalues, h1 and h2. You will get a similar thing, hexagon, but not regular hexagon. Okay, it'll be kind of different lines will be tilted in a different way. That is all. But picture will, and all the things will go through. That the sum of the two, even if you had plotted h1, h2, I mean, if you had plotted all these things in terms of the h1 and h2 eigenvalue, the vectors will look different, individual vectors. But again, the rule of the sums will work in the same way, right? If this was alpha 1 and this alpha 2 in this picture, then alpha 1 plus alpha 2 will be just the sum of these two vectors. And that's all that is needed here, no? Yeah. Okay, so now how does it work then? How much time I have? Oh. Okay. Now, so let me just write, since this was the question. I think the formula is this, we can check it. We can check it with the known examples. But then I think the formula is n1 plus 1, n2 plus 1, and times n1 plus n2 plus 2 divided by 2. So given those integers n1 and n2, the dimension of that irreducible representation is this. Just like in the SU2 case, you had 2j plus 1, but 2j is what I am calling n1. Yeah? So it would be n1 plus 1 in the SU2 case. In SU2 case, there is only one SU2, right? I mean, there is only one x alpha 1 Racine operator. So that is n1 is what we call 2j, 2 times j. So this is 2j plus 1 dimension.
Is there a formula for SU?
Huh?
Is there a formula for SU?
Yeah, I mean, it just becomes more and more. So there's a pattern here. But let's check, I'm not sure, let's check this number, whether it's correct or not. So let's take the three representation, the three-dimensional representation had n1 was equal to 1 and n2 was 0. Because remember the picture was this, right? So again, I just draw alpha 1 and alpha 2 here. And this one was like 30 degrees here, no? The fundamental weights. So this is the highest weight here. Because both alpha 1 and alpha 2 are annihilated, but there's nothing there. No? When you add this vector to that, it comes here, but there is no such weight in that representation, right? Similarly, when you add here, you come there, but that again is not existing. So this is the highest weight. Okay. And now notice that this is exactly, it is the intercept. I mean, if you project it out, it was half here, 1. In our language, it was 1 because this was 2. We had normalized everything by doubling. So this was 2, that was 1, and this, if you project it out, was 1, which is consistent with the fact that this is spin half representation. So here, this will be, n1 will be 1 for this, but n2 is 0 because you see, if you look at this SU2, when you move this up or down, there is no such thing here. No such weight here. The three weights were this and this and this. That's all this three dimension. So if I apply x plus alpha 2, I would go there, but this doesn't exist. So it should annihilate, it should vanish. And similarly, when you apply x minus alpha 2, it comes here, but that also doesn't exist. So n2 is 0. So it's a singlet with respect to that SU2. No? Now if I plug that in here, do I get n1 plus 1, so that is 2, this is 1, and that is 3, right? 3 times 2 and 2 cancels is 3. Okay. Now let's apply for the adjoint representation. Adjoint representation, the highest weight, alpha 3 is the highest weight, right? Because now you see whether you apply alpha 1 or alpha 2, nothing exists there, right? So this alpha 3 is highest weight, and this is a doublet. This guy is a doublet with respect to that SU2, and this 2 is a doublet with respect to that. So both are spin 1 with respect to both, spin half with respect to both SU2s, which means n1 equal to n2 equal to 1. No? So if I plug in n1 equal to n2 equal to 1, you get here 2 times 4 divided by 2, which is 8. Right? That's the dimension of the adjoint representation. So this formula is correct. there's a generalization which just becomes more and more. This denominator is replaced by the factorial. So for SUN, what happens is let me not confuse with this n, SUK, let's say. So this goes like, denominator goes like k minus 1 factorial. Okay, and yeah, here it's it's a slightly more complicated. So here will be k minus, let me write it as k plus 1, SUK plus 1, because the rank will be k. I mean the dimensional Cartan subalgebra will be k. So it's convenient to write like SU. So then it becomes factorial k. So to specify this, I will need k integers. Unlike here, for SU3, we needed 2 integers, right? Because you had 2 SU2s, and this was just telling me which highest weights of those 2 SU2s are. Right? So there will be k integers. So let's say ni plus 1 product I going from 1 to k. Then there will be you have to take the pairs. Okay. So it's always adjacent, and there is a way to where there's a meaning of adjacent. So it is not I and any other j. It is I plus 1. So there is an ordering there. So I have to write n1, n2. There's an ordering there. Okay. Maybe I don't know whether this will become clear by the end of this course, because in order to really understand this, okay, perhaps there's something like there's something called a Dinkin diagram, and from that one can. Okay, there's some kind of ordering of these numbers. So there is this product, again I going from 1 up to k minus 1. Then pairs of 3, I mean 3 pair objects, I plus 1, I plus 2, plus 3. Again, there is this products. All the way up to the sum over all ni's, plus now what will be k. This complicated expression. So I think this is a generalization, but we can look it up. I mean, this should be in any book, in group theory book. I think this is what it is. Product. Here there is only one factor because there's only one combination.
What is the idea for proving that?
Yeah, it's a difficult. I mean, it's difficult. It's not. I mean, this requires a lot of this permutation groups, and which I don't want to go through. That's the reason why I don't want to go through the Young tableau, because the Young tableau I can explain, I can say, but it will be a set of recipes. Okay, and one doesn't understand why those recipes work. But those recipes can be used to take the tensor product and decompose. However, to really correctly understand that, you need to know the permutation groups, the representations of the permutation group. That's a whole different story, and I don't have time to go through that. So there's a lot of permutation group is used here, so to overcome these things. Now, there was something else I want to say here. Yeah, maybe tomorrow I'll just tell you one thing what I'm going to do tomorrow, at least just not tomorrow, Monday, to start with. You see, I said that this N1 and N2, what is specified? Again, let's go back to this picture. So, this picture. And they say N1 and N2 correspond at somewhere here. The weight, that corresponding weight is somewhere here. Then I started this highest weight has, this is the highest weight of the N1 N2 representation. Then I started applying, so here is my alpha 1 and this is alpha 2. So I started applying the lowering operators, x minus alpha 1 and x minus alpha 2. I don't need to worry about x minus alpha 3 because, as we said, x minus alpha 3 is a commutator of these two. So I don't need to worry about it. I can just restrict myself to these two SU2s. So when I apply x minus alpha 2, it will go one step here. I mean, this picture, okay. And you keep applying x minus alpha 1, it will keep going one step back. No? Similarly, if you apply x minus alpha 2s, alpha 2 is that direction, it will keep going like this, different. No? And let's start from here, we apply x minus alpha 2, So unlike SU2, in SU2 there was only one direction, right? Now here is a plane, no? Here are two directions. So okay, this is the highest weight, so it cannot go further that way. Now I apply lowering things. So I go here, then from here I can go there. No? So there is a whole pattern which appears here. So when you do that, I mean, okay, to come here, I have only one way to come here, right? It is simply I apply x minus alpha 1. To come here, I apply x minus alpha 2. There are no two ways of getting here. So since multiplicity of this state is 1, highest weight is just start with the 1 state, the multiplicity here is 1. And multiplicity here is 1. Multiplicity means degeneracy. The same eigen value, but you can have degeneracy, right?
The multiplicity of the whole boundary will be 1.
Multiplicity of whole boundary will be 1, exactly. But what happens here? Here now I have two ways of coming here. I could come like that, or I could come like that. Now, in general, there will be two linearly independent states. But there are some cases, so generally, the general story is that. Generally, this will be two independent states. But in some cases, you find that they are not linearly independent. Okay? It doesn't happen in this case. In this case, it's always multiplicity is 2. But in some other situations where, yeah, I mean, in some situations, in particular, say n2 is 0. In that case, there is no such thing. You cannot apply x minus alpha 2. So suppose n2 is 0. But then I can go here, and then I can go here, and who knows? I mean, so I can go here, I can go here. So to come here, there is only one way, right? I can go here and go there by applying only x minus alpha 1 and x minus alpha 2. Of course, I could come here directly by applying x minus alpha 3. But I'm going to use only these two to label the states, no? To count the states. I'm going to restrict to that. So by applying here and there, I come here. So there's only one way, multiplicity is 1. But now let's go here. Here also, I have only one way to get there. No? Because I just applied 2 times x minus alpha 1. But to come here, I can go like this step, and that step. Or I can go here, this step, and that step. Okay. In this case, you find that even though to begin with you think there are 2 independent states, but it turns out they are linearly dependent. One state is proportional to another state. Okay. So I just wanted to go through that. So I will do that Monday, an example of this, to just show that there is some more subtleties than SU2. In SU2, okay, it was a very simple thing, just one-dimensional diagram. You're just going only one direction, right? But when you have 2 dimension, you have different ways of reaching a point. No? Same thing. I mean, 3 dimension it becomes even more complicated. You know, you have all sorts of ways to reach there. No. So this multiplicity is very important. I mean, it is not guaranteed that there are situations where you may naively count that there are 2 states here, but that is not the case. There's only one state here. No?
If you complete it, then it will become a variant diagram, something like that.
Is it what diagram?
Variant, so variant.
Yeah, I think in one of this. Yeah, I think there also. Yeah. So this formula that finally one gets is include. I mean, okay, this was either for including all correct multiplicities. No? So there are. So you can imagine it's not easy to derive that. I mean, you know, you need to know where what are the multiplicities of various states and so on. It's a little tricky. Okay, so I'll just stop here and. But please don't hesitate. You see, I mean, there is no sense in covering too much material if you have not understood. Okay, so I think more important thing is even if you cover less material, you understand well. Okay, so don't hesitate to stop me. We can review again and again. That's more important. Okay.